So we want to talk about distributional Jacobian for the reason that we may be interested in proving such a theorem. S greater than 0, right? We will see that won't work, but so it's kind of a question rather than a theorem. F goes from the n sphere into R whatever, diffeomorphism, homeomorphism, whatever it is, and then can we rule out, the existence of F going from, so we don't want this guy to exist, Bn to Rn. F on the boundary is little f, and rank of df is less or equal than n minus 1, and now distributional, right? You've seen this, it's impossible if f is CS, right? So we have seen that if we put here almost everywhere, like with the Heaviside function that doesn't tell us anything, so we use a stronger notion, which is more geometric, the distributional Jacobian, so determinant df in this case, right, of some submatrices. So the distributional derivative of f, maybe we can show that at least for certain configurations of Holder spaces, this is impossible. Okay? And this question, if you kind of frame it in terms of the Heisenberg group, is called the Gromov conjecture, right? And if you can solve it, it's you know, many people try it, including Guth and people like this, right? So this is a difficult conjecture that if you just frame this statement kind of in the Heisenberg group. So our hope was that we can get closer. We didn't, but we got some nice results in Euclidean space at least. All right, so this here is just defined by the determinant of some sub-Jacobians. Just write some dash, right? So rank is just meaning that determinants are 0 of, you know, square matrices of size n in this case. And in order to prove that this makes sense, well, we have to define the Jacobian, and then we just said the determinant of df as a distribution is simply the limit as epsilon goes to 0, determinant of an approximation, oh, I was supposed not to write that high, times phi, where f epsilon is smooth, let's say CS approximation. Everything here works in Sobolev space. But it's shorter to write CS. Right, so this is the attempt to write what the distributional Jacobian is, and we saw one argument that said if, so let's put here dimensions, if S is larger than these are n derivatives, one of them we can move over and the rest we can distribute equally. So there is n minus 1 derivatives which I distribute on n guys. So if S is larger than n minus 1 derivatives distributed over n guys, then determinant df applied to phi exists in this sense for any f in CS. Right? This is what we kind of proved with the Fourier transform the last time. We looked at the hand-wavy argument, why we could believe this follows out of Fourier transform arguments. And I said the Fourier transform argument, which is due to Tata in some form or shape, there's a way more beautiful argument that is essentially 2 lines that proves the same statement. Right? And I write down the lemma that we want to prove. We want to look at differences of these things, but since this is multilinear, at the end of the day, we just want to estimate for smooth maps. So the lemma is that determinant df on Rn times phi, for smooth maps, everything is smooth, is less or equal than f in Cs, n of those guys, and phi, the Lipschitz norm. Maybe I'll make this for safety as a full norm, not just a semi-norm. There's a constant here, make a twiggle. So this holds for any s larger than n minus 1 over n. Again, equality can be achieved as well if you work a bit. Okay, so this is the lemma we want to prove. We have seen this, an argument with the Fourier transform. Now let's do an argument via differential forms and extension. Okay, so this proof 2 is, well, in this precise version, it's really in Brazil-Nguyen. There have been like similar ideas, I don't know, people told me about papers in the 70s, but that precise version is Brazil-Nguyen, and it's very cute. One of the most beautiful theorems, in my opinion. All right, how do we prove this? Well, the first idea is we go to differential forms. Determinant of df we can write as a bunch of wedge products of derivatives, right? Let me maybe write, instead of determinant df, I write the determinant of df1, df2, dfn, right? So now I have, okay, these guys, and up to the sign maybe, I don't really care. This is df1, right? We know that's the one form. f1 is a scalar, df1 is a one form. Wedge df2, wedge dot dot dot, wedge dfn. Implicit computation. Okay, and again, I don't care about signs. Plus and minus are equivalent. All right? All right. What does this tell us? Well, this tells us that if we look at the determinant of df1, dfn, and then we have phi, this is the same as the integral. So this here we want to look at Rn. And now the idea is use Stokes and go to one dimension higher. So these Fi's and phi go from Rn to R. So now we extend them. Maybe I call it capital. Fi phi goes from Rn plus 1 plus any smooth, for now, extension. Okay? Okay, this here is a bunch of wedge products. Okay, so this becomes df1 wedge dot 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 wedge dfn, and then we have phi, which is just a scalar. This was on Rn. Now we do Stokes. Again, I don't care about the sign. I go to Rn plus 1 plus, the upper half plane. And Stokes tells me that this is D of this whole bunch. Right? That's Stokes' theorem. And now we do the product rule. Again, there's a sign. I don't care about the sign. D is 0. D is 0. The only way, and that's the same as this distribution and somehow in the Fourier transform case, the D hits the phi. There's no way it hits anything else. Everything else is 0. Right? So this is plus or minus, don't care. df1, wedge dfn, wedge d phi. All right. And that's the full compensation effects. You can prove Kaufmann-Lyon-Meyer-Semmes that Yannick mentioned, right, from that idea. Right? That's the full point of this diff-Kerr lemma. And that's beautiful, right? But why are we done? Well, now it's just Hölder inequality. So we want to estimate this guy. And this is now less or equal than I have these df's. So this is df1 L. We want to have the Lipschitz map here. So we take L infinity here. Everything else gets an Ln. df2 ln dfn ln d phi L infinity. Well, that's an equality. All right. That's true for any possible extension f. Now you choose what extension. Well, this is the Sobolev space W1n in the upper half plane. Maybe I should write this. Rn plus 1 plus. Now we know the trace theorem. The trace theorem says that W1n on Rn plus 1 plus embeds into, and this is surjective, 1 minus 1 over n on Rn, right? That's the trace theorem for W1n. This is surjective. So it means that we have extensions from here into there. All right, we take any extension that does this, and there are many possibilities, right? So for example, you can take the harmonic extension. So we could take something like Laplace f equals 0. So this is the Rn plus 1 Laplace in Rn plus 1 plus, and f is little f on Rn cross 0. That is an extension. It's some convolution operator, right? Which realizes the trace theorem, right? So if you do this, then the gradient f in Ln is comparable on Rn plus 1 plus to little f W 1 minus 1 over n. Right? Because it's a trace theorem. The reason for that is not because there's Laplace, right? The reason is this is a convolution operator. You can also, so this is one option. The other option is take just a convolution. Call this fxt, typical convolution kernel, same inequality holds. Right? Or take a parabolic extension, some flow, some semigroup. All of this works, right? It doesn't really matter what you do. The most rough one would be just take the mean value. It's not really smooth, but this is the way that Gallardo proved this identification, right? That's the extension. Okay? So, take your favorite one, and you can use also Caffarelli-Silvestre one. It's just another PDE. You can pretty much any linear PDE that you extend with, that's reasonable. You can do it. But of course, with the extension, you can choose something special like the normal derivative at the boundary. With the Caffarelli-Silvestre, you recover the fractional Laplace. Maybe here you have other wishes. So you can choose this extending way. Maybe for some computations, it's irrelevant for us. For us, it's relevant. We have this. This f extends, realize the trace. So this here is less or equal than f1, 1 minus 1 over n, and then it's fn, 1 minus 1 over n, and then it is, that's the maximum principle, right? It's the gradient of the normal phi in the L infinity norm. Right? That's the proof. You see, it's very short, one talks a bit less. Okay? So it's very beautiful. And again, you can show that a lot of these commutator results like Koifman-Rochberg bias and all these things, they follow from some idea like this by extension, which is kind of cute. Anyways, so that proves the same statement, this one. Okay? And so what does this tell us? This tells us, we go back here, this notion makes sense, right? So we can even talk about this question when S, maybe not greater than 0, but n minus 1 over n. Okay? All right. Good, fine. Can we prove this theorem for n minus 1 over n? No. we can prove this theorem, or this is a theorem, when S is larger than n over n plus 1. And I hope that should be a number closer to 1, as I screwed up. Right, so this notion makes sense when we have n minus 1 over n. We can prove this statement, I will show you how, when we have S slightly larger. Again, if you know the Gromov conjecture, that's exactly the threshold between what we can prove for the embedding problem of Gromov and what we cannot prove, right? So this here is what we know, this here is what we have. Observe, both numbers are extremely close to 1 if n is very large, right? We are not far, we're not close to 1/2 ever, but okay. All right, so how do we prove, so why, right? Why do we have this and this, not this? Well, the reason is that we need to define the rank, we need this inequality. That means for smooth phi, this makes sense. For applications, to prove that statement, phi is essentially f itself. So we kind of need to distribute the derivatives more uniformly. We cannot have one derivative here and s there. We need to have them all the same. So, just like this, we prove, just see that I don't skip anything. Yeah. So this looks like, the lemma that I prove now is for S larger, and now we have this other number, n over n plus 1, which is a number closer to 1 than n minus 1 over n, unless I'm screwing up. We get this inequality. Everything is for smooth functions times phi is less or equal than f in CS, again, Sobolev version, no problem, and phi in CS as well. I make it a norm because there are some embeddings if we are lazy. And there's a constant in front. Okay, so difference here is I want phi only to get S derivatives, so I have to put more derivatives here. So I see, well, we have n derivatives here. They get distributed among n plus 1 guys equally. That's n over n plus 1. Before, we moved away one derivative and the remaining guys we distributed. So that's the very hand-wavy way to prove it. Right? Just, as a sketch. So if we do the Fourier, the Tatar version, right? What do? We have psi minus eta and eta, and we had these three inequalities, psi minus eta, eta. Then we had psi eta, and then we have psi minus eta. Before, we just interpolated those two. Now we interpolate those three, right? And if we take 1/3 of this, 1/3 of that, and 1/3 of that, so this gives less or equal than eta to the 2/3, psi minus eta to the 2/3, and psi to the 2/3. That's the number of derivatives on phi. That's the number of derivatives on these f guys. Right? And you see this is 2/3. And again, if n equals 2, this is 2/3. Okay? That's the Fourier argument. And so this is Tatar. If you go by Brazis-Nguyen, which is nicer, especially to make it precise, well, we still have it here, right? We have this extension. Now we just take the Holder norm for everybody gets the same. So everybody gets an Ln plus 1, right? And so we get determinant df times phi is less or equal than Then we have these extensions, gradient f in Ln plus 1. I write them as 1 again, times gradient of phi. Right? And again, we use the identification of the trace. Now we are in W1 n plus 1. And so we get 1 minus 1 over n plus 1, which tells us that we have this estimate f in W1 minus 1 n plus 1, which is exactly that. That is what we had before. Okay? Same proof. This is very easy to make precise. I mean, somehow here the difficulty or the subtlety is in that identification to really prove it. Right? And somehow there it's the identification to really deal with the frequencies. Again, it's kind of the same proof. Okay, so we remember this lemma, right? So I claim we can use this lemma for our purposes, and this one we can only use to define the rank. But now let's do the proof. So assume we have an F. We want to show this is not possible in distributional sense. Well, we still have our previous lemma that I didn't prove, which said we have this the form, the volume form, or the linking number of that essentially gives us a link with our homomorphism, right? So lower. So let F go from Sn minus 1 into Rn. Good. Let it be a homomorphism. Then there exists an omega which is super, super smooth in Rn. Omega is close to where F maps into. So d omega is 0 around f of Sn minus 1. Okay. Such that the integral of f star omega, Sn minus 1, is not 0. Now, that doesn't make any sense because f is a homomorphism, right? If f is smooth, that is exactly correct. But the point is, this holds in somehow limit sense. As epsilon goes to 0, f epsilon is a smooth approximation. This is non-zero. Now, this only holds when f is in this fractional Sobolev space that makes that form exist. Right? If not, these numbers are all non-zero. They're all 1 if you want. Right? So this holds, right? Just the limit on its own may not make any sense. Okay? But you can make this number essentially always 1. Although this may not converge. Okay, so this works even for homomorphisms where this thing doesn't make sense for f itself. Okay? So why do we need this this exponent and not this? Well, let's do the proof, right? Let's now prove that theorem like we proved it before, with just Stokes, should be 2 lines. So let's see. So proof there exists no extension of this guy. How do we prove this? F epsilon star omega on Sn minus 1 is the same as Stokes. Everything is super smooth, fantastic. D goes inside, and this is Bn. All right, and now we know that F has determinant, or the entries have rank less than n minus 1, by contradiction assumption. But that doesn't mean that this guy is 0. Right? This here is, if we think of this d omega, maybe we write this as eta, eta of something, and then we have dx I1 wedge p pi n, right? This is this form. So sum over such indices. There is the determinant with this pullback. That's the subdeterminant of f epsilon. But there's this guy. It's a test function, right? So we can write this as the sum goes out, Bn, then we have eta I f epsilon. And here we just have the derivative of some sub matrix of df epsilon, n cross n determinant, right? There's no reason this guy is 0, even in the limit, because there's this guy, right? And we have to test against smooth functions, which are compactly supported. All right, good news. This guy will be compactly supported. Eta is super smooth. So the regularity is inherited also of the convergence of this f epsilon. But we have this condition. We are a closed form close to where f lives. When f epsilon converges to f in, say, CS or in the Sobolev space, we can make sure that f epsilon uniformly converges to f as well, or is at least close enough, right? This is this old computation we had. So in CS or WS d over S, we can make sure that f epsilon of Sn minus 1 lies in the set where d omega is 0. Okay? Because this is essentially, right, it's a projection into the manifold. All right, so this guy, right, the eta I at the boundary of my ball, this here is at the sphere. This is very close to where little f lies, and this guy must be 0. So this guy is indeed in CC infinity of Bn. Okay? Good. But now it depends on epsilon. Right? And that's kind of the issue with the, so far we don't need anything. Now we need to pass to the limit. So we fix epsilon bar, an epsilon less than epsilon bar, and now we just add and subtract the frozen one here, right? So this is the sum. I write eta I f epsilon bar, determinant df epsilon, some subdeterminant, En, plus some En, and then we have eta I f epsilon bar minus eta I f epsilon. Probably screwed up the sign. Determinant df epsilon. This guy goes to 0. Fine, right? Because epsilon bar is fixed. So this is just a CC infinity test function. This is the Jacobian. So this goes to 0 by the definition of distributional Jacobian. So this guy goes to 0 as epsilon goes to 0. This guy also goes to 0 by that inequality. And that's where we need that, right? So this here, eta I is at least Lipschitz, right? So this is less than the Sobolev norm of this guy, which is less by the Lipschitzness of eta I. Then I said I write the CS norm. So we get the CS norm, and then this guy, F in the CS norm to the power n, right? That's this inequality. And for this to be true, we needed that the number of derivatives are distributed to this and this the same way. So S needs to be larger than n over n plus 1. Okay, and then this here, by modification, we have convergence. So this goes to 0 as epsilon goes to 0. Okay? And that proves this statement. Statement way over there. that if the distributional derivative, the distributional Jacobian is 0, and we are above this threshold n over n plus 1, okay, there's no way to extend it. It's a version of a major open problem, right, to lower this exponent, right? So we have the distributional Jacobian 0. Is there a counterexample? This is what I guess people are starting to believe, to the statement that there's no extension. So do we have an example of an extension which is below C2/3 in 2 dimensions that extends, say, the identity with the rank, the distributional rank being less than n minus 1? Open question. Okay? Any questions? All right. Yeah, by the way, what goes wrong? I mean, if you weren't so, why did we do all this approximation? Why didn't we just compute directly and then we get this as 0? Stokes theorem is wrong. Right? Stokes theorem, of course, works on smooth maps by approximation on L1 in the different manifolds. You cannot do that argument without approximation. Right? And that's why, you pay here. Right? I have 2 more things. So of course we can apply this sort of logic or this idea also to the previous degrees type of things. The idea is, right, they rhyme, all of them. They're kind of very similar, but you have to do like a little bit of fiddling to make them work. So let's do this one. Let's call it a lemma. Proposition, I don't know. Assume that f goes from n minus 1. We are back to just map between spheres. N minus 1 to n minus 1. Smooth, non-zero degrees. Statement. There is no f in Ws n over s or Cs, right, with rank df less or equal than n minus 1 in the distributional sense, which extends this, right? F, no restrictions here, Bn to Rn, and f on the boundary is little f in the sense of traces. Okay, well, let's see. Proof. I mean, it's always Stokes. What else do we have, right? So, well, if this is smooth, we have the volume form of the sphere, and we get that f star, volume form of the sphere, is not 0. Okay? Good, now we use the approximation. Right, so this is the limit as epsilon goes to 0 of f epsilon star, volume form of the sphere. Okay? This is all on Sn minus 1. Okay, Stokes, and then we should be done. Epsilon goes to 0. We put the d inside. D of the volume form is just the volume form of Rn, so this is just the determinant. On the ball. But that's not 0. Where is our mistake? Right? There's no reason that this is 0. It's the integral over the determinant. Well, we were stupid by choosing our volume form, right? I mean, the volume form on the sphere, maybe you want to keep that, but the extension of the volume form into the surrounding Euclidean space was silly. We can do better. What do we want? From what we have over there, we want that it's closed to the boundary, right? not just at the boundary. The volume form here is closed at Sn minus 1 exactly, but not in the neighborhood of it. Right? So we want, maybe that was a bad idea. Here is the bad idea. Well, we just project back into the manifold. Right? Instead, right, we take the projection into the manifold. Doesn't exist everywhere, but in a small, I mean, even there in a big neighborhood, but it's, you see that this works on any manifold. So there exists a projection from a small neighborhood of the sphere back into the sphere. That's the tubular neighborhood projection, right? So this is projection. So instead of using this volume form, we could try to use pi pullback of the volume form. Because now when we put anything in, right, or we compute the d, close, evaluated at points which are close to the sphere, then this is 0. Right? So d omega, like this, is 0 for all points close to the n-1 sphere. Because of the projection, right? This maps everything in tangent space. Problem, that's not very smooth, right? Because as we hit the 0, essentially, we get a singularity in the projection. We don't care about that point at all, right? So we take a cutoff function, something smooth that cuts off everything around, so that's 1 around the sphere and it's 0, you know, in the half sphere, half annulus or something. Now, that's a smooth volume form on the sphere itself. It's a smooth extension of the volume form. It's still close to the sphere, and it's super smooth in the whole space. We're in Rn. All right. So that was not a good idea, but all we have to do is think of this as omega, and we have this of omega. Okay, sorry, that doesn't make sense. We have f epsilon star of omega, and yet again, right, the determinant was nicer because it just was the determinant and no weird multiplicative guy. Now we have a weird multiplicative guy, which is why this works only for s larger than n over n plus 1, right? Because again, this is the determinant of f times something depending on omega f. By our choice of omega, this is 0 close to the boundary. Or maybe I call it eta, e omega. So this here is correct test function. Good. So we get that at 0, right? But we pay with that we cannot go below this threshold. Right? So, tiny variation, we have to choose the right volume forms. All right, any questions? Okay. All right. So, one more observation. What we can prove. I mean, there's, you know, Mironescu wrote like a whole book about, well, sort of things like degree between circles and stuff, right? So there's a lot of things you can prove. So remember when we extended the degree the first time, we just had this abstract nonsense result that said everything which is homotopy invariant can be extended to these critical Sobolev spaces, right? When we did that, we had this weird continuity where we said that for any fixed f, right? So we had for any fixed f, there exists a small number delta, which depends on f, such that, well, the degree is integer, so such that if g satisfies that g minus f in this right norm is less than delta, then degree of g is degree of f. Right? And I tell you in application that's extremely annoying, right? This dependency on f. And again, if you're in L infinity category, this is a uniform bound. Right? This delta does not depend, it depends on the manifold. Right? This dependency on f is very annoying. And it's not there for the degree. Right? Well, at least for some s. And again, we see the same exponent. So, lemma. Since we can define the degree via an explicit formula, we can make this here more uniform. Okay? And I do this precisely. For every s, again, this is this n over n plus 1 situation. There exists a delta. And for any m greater than 0, there exists a delta greater than 0 such that the following holds. For every f and g in, I write ws n over s as n minus 1. Any fg in this space such that f minus g in that norm is less than delta, we have that the degree coincides. Okay? And I should add somehow the dependency on f. So the assumption is that we are less than m. Right? So whenever we have an energy bound, we don't need anything about the parametrization of f or anything of that sort. Right? There's no absolute continuity, nothing which is really very dependent on f. And just the norm is bounded. I have a uniform delta that two things have the same degree, if they're close enough. Right? So very strong statement. Proof, Stokes' theorem, obviously. Well, degree of f minus degree of g is, since it's not like an abstract nonsense topologically invariant object, but it has a nice formula, it is f star of omega minus f g star of omega, where this is the volume form. Okay. Now, it's a volume form. We know the volume form. We can make this into one integral, as we have done before, and then we see one f minus g guy, and the rest are f's or g. So this here is less or equal than f minus g, ws n over s. And then we have f plus g. And this should be an n minus 1 form. So n minus 2, but plus 1. So I guess it's the n minus 1. Okay, that's the old formula that we had before. And you see, this is Lipschitz continuity. Right? F minus g is really here as an explicit Lipschitz guy. These are just the bounds m. Right? This is less than m. This is less than m. So if f minus g is close enough to each other, this whole thing is less than 1/2. The degree is integer valued, so they are the same. Okay? So, can you go with s below this thing? In 1D you can, and that's it. Right? It's unclear. I don't even know what to believe, really. Right? If we get this kind of uniform continuity for s less or not, bit unclear. Okay. that's pretty much it. So yeah, I hope I could show you a little bit what I like to think of as cute results, and like an area that combines, a little bit of harmonic analysis, a little bit of algebraic topology, and a little bit of geometry if need be. If you have any questions, let me know. Thank you very much for having me. Yeah. Yeah, I don't know it depends on what you want to look at, right? If you have a formula which for some reason is on a general manifold and involves somehow, yeah. Yes, how to extend it. So, I mean, the degree is between spheres, right? Or things which are diffeomorphic to spheres, which are spheres. Yeah, but that's the thing. If you can test my homotopy class with a formula like this, yes. But you need that formula. I mean, you need the explicit formula of how to kind of decide, how to measure your homotopy class. If you have such a homological formula, then essentially you can extend these arguments, right? So usually the domain, I mean, the applications we have done, right? The domain is the sphere and the target becomes more wild, right? Maybe it's the wedge of spheres or, RP2 or CP2 or something like this, right? Yeah.
Any other question?
Yes. Yeah, it's written afterwards, right? So, well, I mean, you see how it depends on M, right? Pretty explicitly. I mean, this constant in front is uniform. It doesn't depend on degree or anything, right? There's some dimensional constant. It also depends on S. S goes to maybe, right? Possibly to be done uniform, right? But you see here, there's an M, and depends whether I screwed up the power or not. We don't know, I think. I mean, this dependency is likely not optimal. I mean, the power maybe yes, right? But certainly not this relation because that constant is not optimal. Yes, so if I look at this WSN over S, it's really the seminorm. If you're in the Hyder space, you have to be a little bit careful, right? Because you have one Sobolev embedding needs a normalization possibly. Yeah. But only if the oscillation, only at this level S larger than N over N plus 1. It's very annoying. Equal. For the Sobolev space, you can go to equality. For the Hyder space, you can also, but then you have to discuss what you mean by CS. So you take the closure of smooth maps in CS, then you get the CS plus, this is sometimes called, right? So you can go to the limit is clear. It's just the question, it's whether you can go below at all.
Any other question?
I doubt it. I have to be careful. Yeah. So you cannot, I mean, without this, I would be very surprised, right? Because you kind of, so I think of these FNGs as winding around the target, right? If you wind around 100 times and not 100 times over there, they kind of need to be closer to each other to make sure that you really have the same degree, right? Somehow it has to compensate for this 100 times going around, so more things can go wrong. I don't know if that's really the argument. There is a very nice book on the sphere, on the circle, right? The relatively new by Mironesco and Precis, which I assume has a lot of examples and counterexamples. So in the circle case, we have a bunch of results that we don't have in general.